Hi, so today we're just going to talk a little bit about how we're going to handle and how we're handling uncertainties and calibration with the system modeling functionality in the Wolfram language. So today I'm going to be joined by Ankit, who's going to help me a little with questions and comments. So just to brief recap of what's going to happen. Basically, I'm going to give first a very quick introduction to system modeler and the system modeling functionality. Then I'm going to move on to calibration, and then I'm going to show a little bit some application examples in that field. Then I'm going to move on to plotting, and then what the new uncertainty plots can do. And then we're going to continue with a big application example about the Hohmann transfer orbit, which kind of puts these two functionalities together. And finally, we're going to move on to questions, to conclusions, and to some insights about the future of this functionality, and maybe also questions and comments. I would encourage people to check the previous study groups that we have had on modeling. So Ankit run a very interesting one on guiding principles for modeling. This was a very interesting course. It showed the massive power that system modeler has to model all kinds of domains, not only in engineering, but all sorts of domains like biomedical, chemical, social sciences, finance. So this is just to give you like a very good introduction to modeling in all these fields. And also a more fun one, we had one about the aerobatics with very cool planes recently done by Eric Espinosa. So do check that out if you like fun aeronautics with planes. Okay, so this tool that I have here on my right is the system modeler environment. Basically what you see at the beginning is just this canvas where you can drag and drop components and then you can connect them. The power of this functionality is that you can do all sorts of interesting modeling with this with these tools. Basically, here, for instance, I have several components and they are all being connected. The more interesting part about System Modeler is that you can do multi-domain modeling. So, for instance, in this case, we're connecting components that are from the electrical domain with the mechanical domain, and they just naturally integrate with each other. So that allows you to realistically simulate very real-world systems with System Modeler, which is a very interesting feature about this tool. On the Mathematica side or the Wolfram language side, what we can do is we already have some functionality that directly connects Mathematica to System Modeler. So basically, you can query information. So for instance, here I'm asking Mathematica to query all the packages that are inside the Modelica library. And as you can see here, we can see a little bit of the power that we can do, the powerful things that we can do with System Modeler. So for instance, we have components in the electrical domain, we have components in the fluid mechanics, in thermal mechanics, in mechanics themselves. So all sorts of interesting features that come already integrated with System Modeler. But this goes even beyond that because people have already developed all sorts of libraries for the modeling of all sorts of systems. So for instance, we have developed virtual labs on the fields of high school biology, like this one that I have here. So Ankit was in charge of this nice arrangement of content, and it's very intriguing, very interesting. So all of this is possible with System Modeler, and as well with Mathematica, you get twice that power because of course you can query information, you can do all sorts of things with the model. So for instance, here I'm taking one of these models in System Modeler, and then I'm asking for the diagram in Mathematica, and indeed I can just produce it here. The kind of modeling that usually we are performing here in System Modeler is basically based on differential algebraic equations and all sorts of algorithms. But fundamentally, the more interesting part about this component-based modeling is that all of this is done behind bars. So you just have to worry about connecting the components, and the connections themselves are just establishing the equations that do the science and the physics and all the domain-specific equation for you. So this is very interesting because it allows you to very quickly simulate and create all sorts of interesting models. So for instance, here I can ask System Modeler to show me this model of a full robot, all created inside System Modeler. Right. But let me go a little bit deeper into the functionality that we have already available for system modeling. So for instance, here we have, of course, something that you would like to do is to be able to take a specific model and then just simulate it and obtain simulation results. So here, for instance, here I have on the right side, we have a very simple RC circuit, and then I can just directly simulate it in Mathematica, and then obtain an object from which I can query all sorts of properties. For instance, I can ask for which variables have been simulated, and then display them here, or display the simulation results for a specific variable, or to just plot directly the simulation results for a specific variable. So this is, or even more, you can directly, we have already functionality that allows you to extract immediately interesting measurements from your model. So for instance, people that are in the control theory field that might be interested in things like the settling time, the overshoot, and other properties that you can compute with this function called system model measurements. So here I have only shown three functions fundamentally: system model, simulate, system model plot, and system model measurements. But we already have more, and this is growing. Also, once you have the results in Mathematica, you have all the full list of the full power of the Wolfram language to extract and analyze and use the simulation results and analyze your systems and create all sorts of interesting things, all the things that you can do with the Wolfram language, thanks to this interface between the two tools. Right. Just to go a little bit further into this idea of the physical modeling of using components to model stuff. Let me show this with a very simple example. Here I have a model with just a few components. Notice that I have here a component that represents a full motor, and then when I click it, I already get access immediately to important parameter values and initialization values that are relevant to this component. And I get immediately a big short overview of all my modeling, and also I can access parameter values and initial values with their corresponding units. So this is kind of very convenient because I can readily just simulate the model and then obtain simulation results and obtain and model physically a system. Of course, you could imagine, well, you could say, yes, sure, I could also do this just directly by using the equations. But you can see that by doing this with equations, you do lose a little bit of the big picture and interesting parts of your model. You have to be very careful about each aspect of the physics and all the science that is behind it, moments of inertia, etc., that you could get just a little bit wrong. While here, you can just connect components and then you're physically sound model right away. But of course, the two approaches are complementary, and you can obtain results for similar results with the two approaches. But I would just like you to see the benefits of having this kind of overview for systems that allows you to directly approach them and manipulate them, simulate them, and get results right away. Right, so that's on the side of the quick introduction. So from here on, I don't really need you to go into the details of each line of code that I'm writing. I just want you to look at the big picture of the things that we're doing. Then we can go into the details about this in the questions and the comments. But for now, I just want to give you like a quick intro to the things that we're doing. So don't spend too much time looking at each character in the lines of code. All right, let me jump to the things that we have been doing in the last 4 years in the system modeling functionality. Most of it has been focused on getting data to work more directly into System Modeler. So basically, the things that we have had for a while are things like just directly send data to System Modeler and create an interpolation from it. So for instance, if I run this line of code, what I'm doing is I'm taking a time series in Mathematica and then just creating a component that is called my interpolation. So you can see it here. And this component now I can take it and just plug it into any of these models and then connect them, and then directly interact with all the functionality that I have in System Modeler. Other things that we would like to, you probably may want to do with data is, for instance, maybe you don't want to send the whole set of data. Maybe you want to set a specific fit that you have already performed with the statistical with the fitting functionality in Mathematica. So for instance, I'm sending here a fitted model instead of the whole set of data to System Modeler, and I call it my fit. And here I can indeed just drag it and drop it and then connect it to my other components. And another thing that we worked on is, let me just increase the size here a little bit more even. So we worked on also on allowing users to send like a fully trained or fully initialized neural network to System Modeler. So you can just do that with create system model. And then you can indeed, here I have my component representing the trained neural network that I can directly connect to my physically modeled system. So I can get the best of both approaches. So I can get artificial intelligence directly connected to my model if I so wish to do so. So that's the kind of things that we have been working, but also there are more things that you would like to do with data with system modeling. And one of the most obvious things that you probably want to do is to use real world data and then use your model in System Modeler and then make that model fit as close as possible to the real world data so that you can actually get closer to simulate reality in System Modeler. And that's what System Model Calibrate does. Basically, it just uses real world data. You just combine it with your model, and then the function takes care of the minimization problem. It tries to fit as closer as possible your model to the data by fitting the values of the parameters that you think are irrelevant. So for instance, in this particular case, the kind of data that you expect you to to have for real world behavior is time value pairs, for instance, for a specific variable in your model. And then in its more basic form, System Model Calibrate is just going to expect you to provide the variable that it corresponds that data corresponds to, the model, and the parameters that we want to fit in order for the model to simulate that data as closely as possible. And what this function is going to do is just going to create a copy of that model. It's going to use the calibrated parameters in that model. And then you can simulate it and see how closely you get to the real world behavior. There are way more things that you can do with System Model Calibrate. So just to give you like a full picture of all the arguments you can get, you can also specify parameter constraints, which are very important because you probably want, for instance, a parameter to be positive or to be between two specific values, or you want some specific more complicated parameter constraints that must be satisfied by the parameters that you're fitting. So all of these things are possible, and also they are important because that helps you to target more properly the minimization problem. Because basically what we're doing is just reducing the distance between the real world data and the simulation results. So the more information you provide to the minimization problem, the better the function will perform in calibrating your model. You can also provide initial guesses. You can also specify even further the kind of things that you want, the minimization problem that you want system model calibrate to solve. So for instance, you can change the normalization, or you can use regularization. You can change the simulation interval, all sorts of things that you can do if you want to try that. And obviously, since this is the fitting, you probably want to extract all sorts of properties from this fitting. So maybe you don't want just the model. Maybe you want to have also plots that indicate how well your fitting was performed, or maybe just you only want the parameter values, or maybe you want the residuals of the calibration. So all of these things are possible. So we also have an object that stores all these properties. So if you want, you can also just get that object, and then you can just query any of those properties whenever you want to do so. So this is kind of the big picture, but let me just go right into examples so that this becomes a little bit more clear.
Right. Sergio, we had a
Yep.
question
Hmm.
on system model calibrate.
Yep.
So, like, is it only doing least square fit, or what are the different types of optimization uh, like functions is used? And can
Yeah.
we actually
Mhm.
choose different optimization function for the calibration?
Yes, so we can do that. So I guess the simplest thing to do here is to just go straight to the documentation page. And so we have this option that is called norm function. And the norm function directly allows you to modify it. So you can specify, for instance, an infinity norm, an L1 norm. So just to clarify, I'm here, I'm talking about the um, the distance function that we're using to minimize the gap between your data and your simulation. So you can add all sorts of specify the normalization. You can also specify the regularization function. So we have that can also be done with the fit regularization option. And you can choose things like Tikhonov, lasso, all sorts of you have plenty of freedom to modify the minimization problem. Yeah, you can also specify the methods. So all the methods in nminimize and find minimum are available. So you can try them. Yeah, yeah, I think that's the that's what I could say about that.
Right.
Any
Thank you.
other? Oh, okay. All right. Um, all right. So I can just move on with the examples. Right. Okay. So let me just reduce this a little bit. We change a little bit the structure of the right. So yeah. So let's start with the system that I have here. So this is a heating system. So it uses components from the fluid mechanics and the thermal physics library. Um, and what I have here is I have data for the temperature of one of the components, in this case, the heater. And I want to use the data for that variable in order to fit
So if you can
the
zoom in the model, it's very small.
this one. Okay,
Yes.
I'm gonna have to then reduce.
Oh, okay.
uh, okay, like so,
Yeah.
maybe. All right. Okay. So yes, so basically, yeah, we have the data for the temperature of a heating system for a specific simulation where, and then we want to feed the amount of heat that is entering through the burner in the heating system. So in this particular case, for instance, this data is in the forms of a quantity array. So we can obviously handle units because those are intrinsic part of the modeling functionality. And then we just say to system model calibrate, okay, this is a data for the temperature in the heater. And then I want to fit the amount of heat flow that is entering the system. Here I'm just providing us one constraint for the parameter that I'm fitting. So I'm just saying that is between these two values. And then what I'm asking is I'm asking to give me the full object that contains all the properties that I can query from. So once you run this line, but basically what this is going to do is just going to start the minimization problem. It's going to show you a progress reporting on how well the fitting is doing, and then at the end, it's going to show you the final estimate for your parameter value, which in this case is this quantity. Um, from this object, we can
So,
query. Yes,
so Sarji, can we see the temperature data, the quantity array?
sure. Yeah. So it's
So what
this.
basically we are doing here is we have the temperature data from
Mhm,
this model, but the thing that we do not know is how the heat flow or is supplied to the pipe.
mhm.
And using this temperature data, we are trying to get the heat flow, how the heat flow is varying. Is that right?
We want to establish. So this is a parameter. We want to establish the value of this parameter
Okay,
so that this model behaves as closely as possible to the data that we have.
right.
Mhm. Yeah. So
And then you want to, and then we are constraining it so that we reduce the search space, and we give it, it doesn't go, let's say, beyond, it doesn't go to the negative side, or it doesn't go beyond a very big, like, we
mhm.
provided some extremes.
Right, right. Which is always very convenient. It's always very important to help the minimization problem. It's in your best interest to provide constraints. um, yeah. So yeah. So one of the nicest outputs that you can get from the properties that you can get from this object is this prediction bands plot, which automatically displays like a nice summary of how the fit went. So basically, we are doing, what we're looking here is we see in blue the final simulation results. We see in green the original data that we had for the calibration, and then in yellow we have prediction bands with a specified confidence level. So there is a default value for 95% confidence level for these ones, but you can change that as well. Um, but this gives you automatically like a picture of how well the fitting went. And this can be done whenever, so we can compute this plot as long as we have access to the sensitivity um, uh, data for this specific variable in the model. Um, and then you can ask for all sorts of things. So for instance, you can ask for the residuals, and then with the residuals, you can do the kind of residual versus time plot that you may be interested in to also establish the quality of the fitting. Maybe you're interested in a specific kind of noise. So this is also readily available from the object that we compute in the calibration. Mm, right. Um, so this is kind of the first example. Let me jump to a different domain. Here we have a model for chemical reaction. So in this particular case, what we have is a reaction between three substances. We have data for the substance B and substance C, and we actually have several samples in this case. And what we would like to do is use the data for the concentration of the substances to fit the reaction coefficients, the three reaction coefficients in this reaction. So we're going to fit several parameters at the same time. And not only that, what we're going to do is we are not going to use the data for one variable, we're going to use for two variables simultaneously, which is kind of an interesting feature of this functionality as well. You can provide data for several variables simultaneously. Um, so what I'm going to do is, the other thing that we're going to do is, since we have so much data in this particular case, what I'm going to do is also I'm going to split it into data for training and data for validating, which is always a nice practice when you want to do fittings and calibrations. So in this particular case, I'm just, okay, we can skip a little bit the, the code, but basically what I'm telling my system model calibrate is here I have the data for this specific two substances. I have my constraints that I have established here for the three parameters. And then I want to feed those parameters as closely as possible so that the data matches the simulation. And here's the output of the calibration. So as we see, we have these values for the reaction coefficients. And I can ask this object, my calibrated system model, to provide the usual. I want the bands plots. And as you can see here, we see the reaction, the bands plots for the two concentrations. So we see in blue, we see the final result. We see in green the data from the real world, and then we see in yellow the confidence bands. Um, and then in this particular case, yes, so as I mentioned, I wanted to set some of the data for validation, so I can specify later, okay, you can do it before the calibration or even after, it doesn't matter. You can specify some validation data for the variables that you have calibrated. And then you get automatically scores for calibrate, for training and validation. So this is kind of another interesting feature uh, for the calibration functionality. Right. And then I think we have another example, but this time in the electrical domain. So in this case, what we have is something that is called model simplification. Basically, what we have here is just a model that has a speaker here on the right. And something that you may be interested to do is that you may do is just create a different model than the one that you have, but one that is much simpler. So for instance, in this particular case, I'm gonna remove the speaker and then I'm just gonna replace it just by a single inductance. Um,
Sergey, if you can zoom,
yep.
go into the speaker component so we can see what's there inside it.
Oh, I guess we can. Yeah. Okay. Let me change to modeler. Do you mean this, or do
Yes.
you want to?
Yeah, can we go inside? Can we see?
Okay. Right. So this is so this has more
Right.
components.
It has one from the magnetics, I could see one armature component from the magnetics library,
Hmm.
and then it has the resistance and inductance from the electrical library, and then you have a conversion. Okay, so you have the conversion where electrical energy is converted to mechanical energy, uh, right? in,
Hmm.
in the center, in the central part. So
Right.
it's a mix. It's a mix of different domains.
Hmm. Exactly.
Right. and
Hmm.
and then perhaps if you are trying to if you have a big data set, you would want to have a simplified model in this case, then trying to have the complete model.
Right. So one of the reasons in which why you might want to have a simplified model is maybe you just want to reverse engineer some technology, or maybe you need to create a cheaper version of the product so that you can test it against other features. So there are uh, practical reasons why you might want to have a simplified model. But what we would like to do in this particular example is just our calibration functionality. So basically, what we're going to do is we're going to take the simulation results from the complicated model, and then we're going to use them to calibrate the simple model. So we're going to calibrate the value of this inductance so that it behaves as closely as possible to the complicated model. Um, so to do that, I think what we do here is basically we first just simulate the models as they are, just to see how different they are. And here we can see a little bit of the comparison. So they are not doing very well right now. But what we're going to do is just we're going to, as I said, we're going to extract the simulation results from the complicated model, and then going to pass them to system model calibrate. So I'm going to say, I want this variable in my simple model to behave as the complicated one. And then I want to feed the value of the inductance.
So what is
Mhm.
what is this raw data function that we are trying to, or what is this raw data option that we are using?
Right. So, but here, so raw data so when we simulate a model in Mathematica, what you generally get is a system model simulation data object. I think this is probably still available here. Let me get this here. Yes. Right. So this is the object that stores simulation results in Mathematica. And then you can extract the simulation results for a variable in several ways. So for instance, you could extract it just as it is. So usually this is going to be, it could be a single interpolating function, and it could be a piecewise of interpolating functions. It could be a relatively complicated one. But in this particular case, what you generally want is just time value pairs. So you can just specify that you want the raw data for that variable. And then what you're going to get is a list of time value pairs that represents the simulation results for that variable. So it's convenient because in calibration, generally you work with discrete data like this instead of like continuous. So that's why we're using here the raw data property. Yeah, yeah. And that's what we're passing to system calibrate here. So I'm just giving these time value pairs to this variable, specifying the constraint for the inductance, and then asking system calibrate to calibrate the value of the inductance, just to simplify that complicated model. And then it gives me a value for the inductance. It gives me this 0.5 Henrys. From that, I can just extract the simulation results of the calibration and then compare it with the original model. And now we see that they are behaving much closer. So we have successfully simplified the model in this particular scenario. Right. So that's in the side of calibration. I'm about to move on to the side of plotting. Not sure if there are any other questions or comments that maybe we want to cover before jumping.
Um, there
Mhm.
is one question. Like, like can we do sensitivity analysis of our models using the Wolfram language? And if yes, can we do something like a global sensitivity analysis like Sobol indices? I actually don't know about it, but
I see.
like,
Um,
for
okay,
sensitivities, what can we do using the
right.
Wolfram language?
Right. No, that's a good question. I'm actually gonna about to jump into a little bit into that. I'm gonna have an example here precisely with the functionality for sensitivities.
Right. Okay.
So that's a good moment for that. I'm gonna mention that briefly once that comes out. Um, so maybe I can just go into that now, and then maybe we can. And I don't
Yes.
know if there are, yeah, okay.
Yes.
Right. So we have this model here of so in here I wanted to show a little bit of what's available for plotting before we introduce the uncertainty plots. Um, so I have this model here of a motor, and I'm just going to use it for a few plotting scenarios that you may be interested in. So one thing that you may be interested in is just to just plot a specific variable. So I have shown this several times now, but maybe you want to specify a specific parameter value for a parameter in your model. So this you can do inside of system wide plot. So that's what this is doing. So this is plotting this variable, assigning this specific value to this parameter. So that's what this is doing here. Another thing that you can do is you can just do a parameter sweep. So you can specify several parameter values for a specific parameter, and then what we do is we plot the results for all those parameter values. So we simulate the model with those parameter values, and then we plot the
Right.
results.
So in this case, Sergio, on the right
Uh-huh.
hand side, we have a DC motor model, right? Can you just quickly explain, like, what are those components, and what is the inertia one and inertia two that you are showing?
Right. So here I have a bit of a motor. Basically, here we have a small
If you can zoom
circuit.
in, Sergio, it's you can close the component browser, perhaps. Okay, this is fine.
Uh, sure. So we have the the a small circuit here, and then that
The
energy can be
electromotive, yeah. The
yeah that energy can be transferred as mechanical energy with a EMF, and then here we have inertias. So here what I'm plotting is the angular velocity of this particular inertia, the inertia 2, and I'm modifying this parameter value j for the inertia, which I believe is okay, this is a good use case for system modeler. So j, which is I believe
J is the
uh,
inertia of right.
right. Yeah, I think it's just a moment of inertia. Yes, a moment of inertia for the inertia. Right. Um, right. Yes. So yes. So this is the situation. Basically, we have a model here. We are plotting a specific variable, and then we're modifying the parameter values. Um, and then what we're doing with what we can do with sensitivity here. So this is another thing that we already had available. With sensitivity, what we do is so we have some functionality inside the simulation kernel in System Modeler that can compute first order sensitivities for specific variables, for state variables. Um, and then what we do is, so we produce that simulate the sensitivity data with system model simulate sensitivity, so a different function from system model simulate, where you specify, okay, I want to simulate my model, but I also want to compute the sensitivities for state variables with respect to this specific parameter. So I'm specifying a parameter there. Um, and then what you can do is then plot the sensitivity bands. Basically, what this is telling you is so have the original results, and then what we can compute is you can specify a specific percentage that you want to move away from the result using the estimated sensitivity for the for the model. So at the moment, the sensitivity analysis that we have available is just the one that exists in the simulation kernel, which is limited to state variables, and it's just it's um, it's a work in progress. so so that's what's present there. Mm, right. So this is kind of the thing that we have there. And then we have also a resource function that is called system model manipulate. So what is nice about this function is that so this is a function that lives in the function repository, and it's a function that you can use just to pass a model, and then you can specify the things that you want to control for the model. So for instance, just to follow the same example that we've been using, I'm using the same motor model, and then I'm telling a system model manipulate that I want to manipulate the parameter that we have been changing in all of these examples here. Um, and then what this system model manipulate is going to do is going to build the model, simulate it, and then create a manipulate around it. Um, that is going to allow you to just modify the parameter value and then resimulate and then compute the simulation results and plot them. Um, So this is just to show you the things that were already available for plotting. But recently what we added is, okay, we wanted a feature that would actually consider and would take into account the possibility that, well, the very important feature that our systems in real life actually have uncertainty. So these parameters could be uncertain, initial values could be uncertain. So that's the introduction for system model plot system model uncertainty plot, which basically tries to capture this. So you have a system, and then your system usually has certain uncertainty for parameters, certain uncertainty for initial values, or even you can have uncertainty in inputs. So for instance, your parameter can follow a specific distribution, a statistical distribution, or maybe your initial value, you only know that it's in a specific region or geometric region or in a specific interval. Or maybe you know that your input follows a specific random process or a stochastic process or something like this. And then you want to take into account all of these sources of uncertainty when you plot the variables in your model. So what is this uncertainty doing for the variables in my system? So what we do is we try to sample all of the sources of uncertainty. We aggregate the data, and then we produce in the by default what we do is we just compute the median and then some quartiles, just to show how this output behaves in time, so how the distribution changes in time for the specific thing that we're plotting. So just to follow the same example that we have been doing, let's take the hybrid motor, and then let's specify that the parameter that we have been modifying doesn't have a specific value. It instead just, we only know that belongs to a specific interval. So this is a center interval. So it just says, I just know that this parameter is in the 2 ± 1 center interval. And what we do, what system model uncertainty plot does is just it just simulates this. So by default, it just performs 200 simulations, um, and then aggregates the data from the 200 simulations, and then computes the median and the quartiles just to show how the output is actually changing in time.
And
Um,
this 200, that is, we can change it, right, as well. Like,
uh-huh,
for example, we can have small simulations if I need, and we can have more simulations as well.
exactly. Yes. Right. So well
So
that.
what you're doing here, Sergio, is like you're taking a model, and then when you are defining, let's say for the parameter value, a centered interval, so you're sampling 200 different values for inertia 2 dot j, like, and then you are doing 200 simulations,
Hmm.
right?
Right.
And
Yes.
and you used a centered interval, but you could
Hmm.
also use, let's say, a normal distribution and other distributions as well.
Right, exactly. So let me show you a little bit here in the documentation what this goes through. So yes, so you can provide intervals like interval or center interval.
If you
You
can
can
zoom
just
in a bit, Sergio.
yep. Right. Yes, so you can provide. There you go. So you can provide an interval or a center interval that is going to be sampled uniformly. You can provide an around. So an around is like a fuzzy version of an interval, basically a normal distribution around the value. Maybe I can show you later. Or you can just specify a distribution. We have a massive landscape of distributions that you can choose from in the statistical distribution functionality of Mathematica. You can just provide a geometric region and we can just sample it uniformly. Or you can just provide a specific custom list of values that we can just sample randomly. All of these are possibilities for the parameter values and the initial values. For the inputs, you can provide random processes, as I mentioned, or custom lists of inputs that you want to sample. Um, right, or just a single input. Right. So yeah, so it's there's a whole landscape of possibilities here that you can use here.
Right. And when you said inputs, for example, let's say I have a model of a solar power plant, and
Hmm.
I want to plug in the solar radiation as an input, and because of the cloud cover, the solar radiation is not certain. That may be some stochastic involved in it. So those kind of
Right.
things I can add as an input, right?
Exactly. Yes. So for instance, right. So for instance, in the scope of random processes, we have all sorts of random processes. We have white noise. We have stochastic processes like the ITER process. We have a whole landscape there of possibilities. Just so that you can use as uncertainty. But let me show you that in the specific examples here in the presentation. Right. So as I wanted to say, yes. So by default, we just show the median and the quartiles for the distributions of the output. But you can also specify different kinds of slicing. You can also specify that you want instead confidence bands, or you can specify your own slicing if you want something more custom. Um, right. So uh, okay, since maybe I'm gonna skip this first example because it's a little bit too basic. But for instance, an interesting example here is again with the speaker model. Um, Here, what we have is it's not uncommon that you want to say that the components in your product actually have specific tolerance. So, for instance, the resistance maybe in these particular cases you can just specify that your resistance follows a normal distribution. Usually, this is actually a truncated distribution because it doesn't take negative values, for instance. But then you can specify that this is the distribution for your resistance in your in your system of for a speaker. And then we can just compute the uncertainty plot for this situation. So we sample this distribution for these values of the resistance. We compute the 200 simulation results. We aggregate them, and then we display how your system behaves. And then you can say, okay, maybe this behavior is acceptable for me for my product, or it isn't. It depends on the safety measures and tolerances that you can accept for your specific product. Or maybe you want
So
to
Sanjay, if
say,
you can
yeah.
explain a bit on the truncated distribution, like what is it trying to do?
Basically, what it does is just so basically here, what you can do with that truncated distribution is you can say, actually, my distribution doesn't live in the full space of the real numbers. It actually just belongs to specific region. So here I'm saying I want the normal distribution, but I only want to truncate it to positive values, so from 0 to infinity.
Right, because
Um,
resistance cannot be negative.
exactly. Uh-huh.
Right. Okay.
Right. Um, yeah. So right. So for instance, here I have. Another possibility is that maybe you want to test your system against disturbances in the environment. So, for instance, maybe you want to see, actually doesn't my speaker. I want to test my speaker with an electrical outlet that is not completely reliable. Maybe I have some high frequency noise or something like this. So I can use that. I can say, okay, my input for my system is not actually like a single sinusoidal trajectory. Maybe it's just a very noisy signal with high frequency noise. And then I can use that to test my system in a different way. So for instance, I can say, actually, my speaker is going to behave in this way if there is some noise in the signal. And then maybe this is significant or not significant, or maybe this is not problematic or problematic for my system. But at least I get a more complete picture for my product in this particular scenario. Right. Let me just jump a little bit because we are kind of reaching the end of the hour. So let me just go a little bit quick over the final example that I wanted to show. Um, and so this particular case is just um, a quick example of an orbital maneuver. So in this scenario, what we are going to do is we're going to use. We already have a model of a chip um, performing a circular trajectory in a gravitational system in System Modeler. So I'm just going to use that model and then try to do something more interesting. So here you can see that the model that we already have in System Modeler is just a chip that is doing a circular trajectory. By the way, the animation features are already something also nice that you get from System Modeler. You can get this directly from your model. Um, and then what I would like to do is to do something more interesting. What I would like to do is to change the trajectory of this chip. So maybe I want to change the radius of the trajectory and just keep it still in a circular trajectory. What I'm going to do here is I'm going to create a model that tries to perform something that is called the Hohmann transfer orbit. Basically, what it does is just uh, performs an engine burst at the very beginning of the simulation. So it just pushes the chip a little bit forward. That puts the chip in an orbital trajectory, and then after as half of a full trajectory, it just does another push, another boost, and then that settles it into a circular trajectory and leaves the trajectory that you hopefully want. So you want to do a push here and then a push here. Um, and then, so in order to do that, what I'm going to do is, okay, I'm going to skip a little bit the details, but basically what you do is you just create a model that performs the two boosts. Basically, I'm here just using a piecewise function that just has a boost at the beginning and a boost later. And I'm going to calibrate the magnitudes of those boosts in order for the trajectory to actually end up being circular. Um, so in order to do that, I connect the boosts to my chip. First, I can try experimental a little bit with the magnitudes of the boosts. So for instance, if I try with these magnitudes, what I see is that generally I'm not going to land in a circular trajectory. What I'm going to land is going to elliptical, and then I'm going to end up very far from the planet in some situations. But what I'm going to try to do instead is, oh, okay. And then if I plot the radius as a function, then I see that for these specific choices that I made previously, I'm definitely not landing in a constant radius trajectory. So as here I have my original trajectory, which is just like a circular trajectory, and then here my radius is just like changing very wildly. I want this to be just a constant line here. So none of the choices were good, but what I'm going to do is I'm gonna use system model calibrate to solve my problem. So to do that, I'm gonna create some artificial data that I'm gonna pass to system model calibrate, and the data what is gonna I'm gonna give the grossest approximation to the change in the trajectory. I'm just gonna want the radius to change to a say a certain value and then stay there. So of course the physics is not going to allow this specific trajectory, but I'm just going to ask system model calibrate to approach this behavior as closer as possible. Um, and that's just what it's going to do. So I'm going to take that target, I'm just going to extract some data and then do some calibration. So I just do my general system model calibrate call. So I'm just passing that data for the radius of my new trajectory. And then I want to specify that I want to calibrate the values of these two boosts with some specific constraints here. So I run my calibration, and what I obtain is these values for the two boosts. So I then plot how the radius behaves after that calibration, and then what I get is this blue line here. So as you see, this is getting much closer to what I was hoping for, which is just a nice change between some radius at the beginning and then some radius at the end. And I can actually put the two models together and see the animation. So this is what I have here. So what I see here is in blue I have my original trajectory, and then in yellow I have my calibrated trajectory. So here I have the first boost, and then once it gets here, it gets the second boost. So now ideally my chip is gonna do a full trajectory. Um, and if everything goes well, then hopefully it's gonna now land in a nice circular trajectory, um, which is strider. Um, so that's just kind of one of the nice things that you can do with system model and calibrate. Of course, you can plot this in Mathematica, and then something that you can also do is you can experiment a little bit. So you can ask system model uncertainty plot. Well, maybe what if I got the boost wrong? What if I got one of the boosts wrong for a certain amount? Maybe my boost was actually in a given interval. And then you can get a picture of what could have happened. You could have ended in very wild orbital trajectories that maybe weren't what you were hoping for. And finally, you
Also,
can.
Sergio, like during
Yes.
this entire workflow, it was very nice. But
Uh-huh.
one thing that you actually showed, but you didn't
Uh-huh.
mention, is you created all these models programmatically using the Wolfram language.
Right.
Uh, like you rather than dragging, like in some applications, rather than dragging and dropping,
Hmm.
you actually used Wolfram language to place and connect components uh, programmatically,
Hmm.
right? That was
Right.
I think interesting, and I think people would not know what you did there.
Right. Yes, that's another possibility. Yes, that's another feature that we have in the system modeling functionality. You can use functions like create system model that I used at the beginning to create the system model from the piecewise. Or you can use a function like connect system model components to connect components from Mathematica, which is convenient in some cases. In some scenarios, it's convenient when you want to do some programmatic model creation. That possibility is always available there in the
Yeah,
Wolfram
it's
language.
basically when you have large scale models, and rather than
Mhm.
dragging and dropping, let's say 100 components, you could
Mhm.
actually use Wolfram language and connect them sequentially. You could of course do it in system modeler using loops, but I think it's convenient if you could do it with Wolfram language.
Right, exactly. Yep. And I think the last thing that I wanted to show for this particular example is that you can even use this background of the uncertainty plot, and you can put it as background of your manipulate. Uh, but maybe that's going to take a little bit of time. So,
So what you're trying to do here, you have
mhm,
the system model manipulate. You have
right.
specified the two parameters that you want to modify. You have
Hmm.
given a starting point and then a range for those
Hmm.
two boost forces, and you have specified which plot you want to plot. You want to plot
The radius.
the radius difference
Hmm.
in some way, right?
Right. And then I have saved this uncertainty plot in this variable uplot,
Right.
and then I can overlap them one over the other. Um, just give me one sec.
Could you use epilogue or prologue for this as well, or uh,
I think yeah, I think that's probably also a possibility. I decided to just use show, but yeah, yes,
okay?
that's also a possibility. Just use one of those. I guess.
Yes. While this is happening, Sergio,
Uh-huh.
there was a question, like
Hmm.
how do you calibrate on a matrix of data?
Hmm. So
Uh,
what? Uh, is it just so? Is your matrix of data is well? Okay, because that depends on the question, right? Because if your matrix of data is just several simulation results for a specific variable or for several variables, then you can just split it with the Wolfram language and then pass them for each specific for the given variable that you are working on. Or maybe you are doing this for, or maybe this is just simulation results for a single variable, and then you can still pass it directly to system model calibrate. So in the example that we did for the chemical reactions, we actually had several measurements, so like 50 measurements for the symbol for the same variable. So when we were just doing that case, in that case, we just flatten them and then pass them directly to system one calibrate so that they can do the calibration. But maybe they're meaning other kind of data, in which case they cannot just follow up with that different question, and then we can answer them. um, yeah, so here this is what I wanted to show. So here we have as a background the uncertainty plot, and then as I change the values of the boosts, I can see how am moving in that space. The space of possibilities that I could have gotten for the trajectory of my chip. Um, some a little bit
this
wilder
is
than others. Yeah,
this is not what you would expect.
yeah. This is what this is what you don't want. Exactly, for the chip to just go out of your plot. Um, yeah. So let me just follow up a little bit with just the conclusions. Very quick. So basically, this is just functionality that we're working on to improve the flow for calibration and validation of systems. So the idea is to get your systems closer to reality. That's what we want. The uncertainty analysis also gives you an idea of a way of in which you validate your models and analyze them in a more complete way, just to get a picture of what happens if things are uncertain in your system, which usually they are. And then what we want to do for the future is just explore uh, more interesting functionality for validation. Something that is going to be available readily in 14.1 is the possibility to plot expressions in system model plots. So for instance, here let me come back to my usual simple model of an RC circuit. And then I'm just, as I have shown several times, system model plot allows you to plot specific variables. But now in 14.1, what you can do is you can even add expressions here. So maybe you are not interested in the actual behavior of the voltage in the capacitor. Maybe you only care about when the voltage is less than a specific value, or any complicated requirement that you may want to ask for. And now we can plot those kind of things with system plot. So this is kind of a quick window into validation for simple requirements. So as I can show you with the plot, right. So for instance, here we can see that for values between these two times, the voltage in the capacitor is very high. So between this time and this time, this requirement is not satisfied. So that's why we're getting a false here and then a true for all these other times. So you can plot a set of expressions. In this case, it's a Boolean expression, but this could be any other kind of expression. So this is a functionality that is coming out in 14.1, and we're working on something way more advanced for 14.2. So
Right. So
that's
basically, one
mhm,
could use this kind of functionality to programmatically test, let's say, thousands of different configurations, and
mhm,
then you would get back only the configurations which meet certain criteria, and you
right.
don't need to manually go and test the simulation results for your thousand simulations.
Exactly. Yes, that's where we want to head on. Right.
Yes.
Mhm,
Okay. Um, right. So there's a question that
mhm,
like how system modeler is different to console, and how system modeler is different uh, like than Simulink.
mhm.
Um,
I think you may be more a better fitted person for that answer, actually, Ankit.
right. Uh, yeah. The thing
Mhm,
is, first question is like,
mhm,
uh, so system model is not only for signal processing. So if you
mhm.
open the speaker model, Sergio,
Yep.
uh,
Actually, I
so
can
there
see.
you have a multi-physics model as well, where you have combined uh, the electrical domain with the mechanical domain, and the magnetics domain as well. So you can combine different modeling domains in system modeler. And as Sergio said, when you connect to components, you are not just connecting like an input with an output. You are actually taking into consideration the Kirchhoff's circuit law or Kirchhoff's voltage law, and those mass conservation and energy conservations are taken into account. So it's just not the passing of signals, but of course you can do signal processing applications using system modeler as well. Um, but but that's a separate tutorial on system modeler. Also, when comparing to COMSOL, now we are also working on. So system modeler is for lumped modeling, right? You can of course discretize a component and create um, more finite. You can create a FEM-like model as well, but it's mainly for lumped modeling. But now we are also working on integrating the Wolfram language and system modeler. So in the Wolfram language, we are working uh, with the different types of um, FEM modeling approaches, and we are trying to see if we can integrate some learnings between FEM model and system modeler. So you can use a system model to get boundary conditions, and that boundary conditions you can use in your FEM or CFD models, and then a- and then use it like that. Or you can use a FEM model and then you can create a state space matrix, and that state space matrix you can convert into a simplified model that can be plugged with your other system models, right? And if you want to know more about the PDE modeling and the system modeling, we have two different community posts in the system modeler group. Sergio, like if you can can explain on this FEM and system model integration part a bit. Uh,
Okay. So, who has been mainly behind this effort is Vedat Sanal, but to give a quick uh, summary of the things that I think they have been trying is basically all of these structures, all of this modeling that we have been talking about. This can be approached in different ways, as Ankit mentioned. It could be a lumped modeling or a more um, of modeling with bigger granularity, like a FEM kind of approach. So in what we do is we use Wolfram language to analyze this from the point of view of the PDE modeling. We can extract specific structural parameters from the simulation, from this kind of solutions to the PD problem, and then this information can be passed to system modeler to create more refined models that follow more closely the reality and take into account more closely the structural properties of your system. So this is what is being done here is also going in both ways. So you can either take your lump model and then use the information in your simulations to create a more interesting PD model in Mathematica. Or you can go the other way, which is in this case, take the properties, the structural properties from your PD modeling and then create more refined models, more refined lumped models in System Modeler. Um, right. But for more details, I deeply encourage you to go through the community posts. They are very interesting.
Right. So, Sergio, some final words on if people have queries, how can they how can they ask us, and where to learn more on the different, because you covered a lot of things
Mhm.
during the presentation, just to give an idea of what is possible, uh,
Right.
and where to learn more, and if
Mhm.
they have queries, how can they reach us?
Right. So for this specific webinar, you can just use the community post to ask questions. But if you want to understand the functionality that we have here more deeply, I deeply encourage you to again to go through the study group that we had a couple of weeks ago, given by Ankit. Very very interesting. It goes into deep about all the things that you could do with System Modeler, several with several sessions. Very very interesting. And then you can always reach out to us by email. The Wolfram functionality, the system model functionality can also be found in the as the rest of the Wolfram functionality in the in the Wolfram reference page. For system modeler, we also have a documentation center where that gives you more information and insight, and you can always reach out to us by email. We are very friendly and happy to help.